Hi everyone, my name is John. Thank you. I'll get started. Thanks for the encouragement applause. My name is John Kısagun. I'm one of the co-founders at Enigma, and I'm also the Chief Product Officer. It's very exciting to be here today to share this event with you. We're going to talk a bit about, so I'm going to do an intro, just we mentioned all about developers here. I'm not one, so I'm going to keep it short. I'm just going to give an intro on who we are and why we do what we're doing. And I'm going to pass it over to Fred, who will go over the details of our network, actually like the next release that's coming up. And it's very exciting because we have never shared it publicly yet. So it's very exciting to share it with you and hopefully get feedback from you. Looking forward to it. Cool, so let's get started. So at Enigma, we're building the privacy layer for the new internet. And I'm going to tell you a bit about what that means and why that's important before I kick it off to Fred. But just to give you some background, we started our research in 2015 while we were students at MIT. And at the time, we were all very intrigued by the idea of decentralization. And we got into blockchain research. And soon after, we realized while blockchains are a very innovative technology, it kind of falls short in terms of full decentralization. And that's because blockchains are made for correctness and decentralized trust, but that comes at a cost. Cost being this notion of data has to be visible to everyone. This creates we believe this creates major problems in terms of future adoption of this technology. And I'm going to give you two examples. One from something that we currently see today, and one of a more longer term promise that people talk about. The shorter term approach is around governance on blockchain projects. As you know, voting becomes a big part in most of these protocols when decisions have to be made. But one problem with governance as is right now, whenever there's a voting that takes place on these protocols, Ethereum had one about the mining reward, had one about the DAO refund, right? All the votes you're casting are visible to everyone. That's not ideal for anonymity, but it's also actually very dangerous because if I at some point know what way you're voting, I can create a contract and fund it so that as long as you vote the way I want you to vote, you'll get some money. So this becomes, this makes bribery contractual, and as you can see, it's like very, very it doesn't work for a well-defined governance system. And then, like more so on the longer term, people talk a lot about blockchain being the holy grail, like that would give people control over their own data, or the fact that it can disintermediate these middlemen in the marketplaces that we see, such as things like Uber. But like if you think about potentially having a social network on a blockchain, all your friends, all your interactions, everything you do is visible to everyone. And if you're doing something like an Uber on a blockchain, then your location, your destination, how much money you have, whoever you transacted with, all that becomes publicly visible to everyone. And that becomes more of a kidnapping app than a transportation app. So that is the limitation that we see with blockchains, and we're trying to work on the solution that would enable privacy for true decentralization. What we're building is a privacy protocol that enables computations over encrypted data. That means you never see what data you're working on, but you can still run an analysis and reach consensus on the result. We're introducing this concept called secret contracts. Secret contracts are very, very similar to smart contracts that we know from Ethereum. The only difference is the inputs that goes into that contract do not have to be visible to the entire network, but you can still reap the benefits of all the decentralized, all the promise of blockchain without oversharing your sensitive or private data. The way we do it is by leveraging two different techniques. One is called Multiparty Computation, which I will refer to as MPC, and the other one is hardware-based trusted execution environments. We started our research with MPC back in the day. However, this first version of our network that Fred is going to introduce is based on trusted execution environment. And that was a decision that we made so that we could target a broader range of applications and get something out there that people can use faster. That said, MPC is still a big part of our network security. We're using MPC for our key management in the current version of the network. And in the future releases, we'll have secret contracts that are powered solely by multi-party computation. With that, I want to give you some color on the kind of projects that we're working with and what's exciting to us right now. I already talked about governance and why we believe privacy is key for governance. We're working with projects like Aragon, Civil, Crypto Against Humanity, Ocean Protocol, to help them better do governance on their projects. We are about to start a working group around what's going on. In the meantime, any questions around what I discussed so far?
Oh, is this public or is this private? Is this permission?
It's private. It's public.
Oh, so it's on Ethereum?
Right now we're still testnets, but yeah, the idea is, so all I'm telling you is technically we are building right now as a sidechain to Ethereum.
Give us a second, we just need to switch the source station.
Yeah, and then the reason, can you guys do that? The reason why we're doing that is because like there's a lot of activity on Ethereum, and we would like to tap into the use cases that we see there, because people are actually building things there. And our goal is, right now we see a lot of decentralized application developers who build on Ethereum and then use Amazon for like certain things that they cannot have on Ethereum. And the goal is to be a side chain where you know, you can run computations that require privacy on Enigma network while the main application is deployed on Ethereum, and you add a level of decentralization and you're not stuck to things like Amazon.
So it's like a side chain?
It's a side chain with consensus. It can be its own chain in the future. That's the way to see it. Okay, so yeah, I was talking about governance. So we're starting this TCR working group. Who here is familiar with TCRs? Okay, so TCRs are this concept where you create subjective lists, and the management goes to a voting structure. So we're working with a bunch of projects that want to define how their TCR should work and want to have private voting there. Auctions is an area that we're interested in. We believe auctions are going to be key when NFTs become more popular. But currently, there's a company called Portal Network that is doing auctions for ENS, Ethereum name domains, and they are implementing our secret auctions contract. And with auctions, you can actually do, basically like when you can do auctions, you can build order books, and you can do private exchanges, which I'm going to talk to you in a bit. We're very excited about gaming in general. Right now, any card game you play, you have to have the deck hidden. You can't really do that right now. So things like blackjack, poker, whatever you have in mind, or also like games where you have to go to a place and like figure out the reward. You don't need to, like you obviously don't want to know what that reward is before you get there. So we're having conversations with projects like Loom Network and Decentraland around enabling them implement some games that they cannot currently do on Ethereum right now. Identity is very interesting. We're working with this company called Data Wallet, and what they do is they take your Facebook data and they own that data, and they run some algorithms on it to determine with some confidence whether you're a human or a bot. So what we're enabling them to do is we're turning that algorithm into a secret contract on Enigma. So your data doesn't go to this company, but it runs into our network in an encrypted way. We can still run the computation and let you know whether you are, or like let people know whether you're an actual human or a bot. And that becomes interesting for people who are running ICOs and want to limit bots, or people who run games and want to make sure that one person per game is possible. Private exchanges is something very interesting. I mentioned this in auctions. Basically, if you can do two-sided auctions, you can create a secret order book. But what's more interesting is you can also do post-settlement privacy with Enigma, which means like you don't have to know who traded with whom. You just like know these trades are taking place. And then the last idea, which is a bit far-fetched, and I think we're a bit early for that, but you can create this concept called a secret ICO. The state of the Enigma network is encrypted. So you can run an ICO, or like you can create a token, let's not call it an ICO. You can create a token on the Enigma network, and the token will have Zcash-like properties. So it's very interesting for people who want to build privacy-preserving tokens on us. And the reason kind of why I went to all this is my role at Enigma is to identify these use cases, find teams who are working on these, or encourage people who want to work on these, and then work with them basically to help them get to where they want to get, because at the end of the day, our success metric is to have these things be built on our network. So with that, I'm going to pass it to Fred, who will get into our network and more technical details.
Okay, my name is Frederick. I'm an engineer with Enigma. My goal here is to sort of give an overview of the architecture of our network. This is something that's still a work in progress. Essentially, like the architecture that I'm describing is something that we're currently working on and building, and obviously, like we're still making some adjustments as we're building the different pieces. And also, like, it's going to be pretty informal. It's the first time that I do this presentation, so you know, I'm not sure that I have it down very well. So it's going to be pretty informal. It's going to be me walking through some diagrams, and then you guys can stop me at any time and ask me questions. So essentially, like, the level of granularity that I'm going to go to is largely going to depend on your questions. So don't hesitate to stop me and ask anything you want. Okay, so this diagram here describes what we call our MVT. So one or 2 months ago, we released this MVT network, and our attempt with doing that, or our goal with doing that, was to release kind of a proof of concept. So we created this simple network which uses SGX enclave to run computations. So as John mentioned, at the moment we're running private computations using SGX enclaves, not yet secure multi-party computation. And the goal of this MVT is to kind of prove that, you know, this can be done, and kind of work out the details on how to do it. So basically how to use Ethereum in conjunction with Intel's SGX remote attestation process, and come up with a coherent architecture to essentially be able to run Ethereum computation on SGX and submit some proofs and make sure these proofs are verifiable and stuff like that. So this is what our MVT focuses on. The implementation is fairly simple. It can run computations that are included in functions of smart contracts deployed on Ethereum. So you could take your existing Ethereum smart contract and take one of the functions of your smart contract and encrypt some inputs, like on the user's side, encrypt the inputs of this function, and then specify that using a client library and dispatch that to our network. And then our network is going to take this set of instructions, locate the smart contract, locate the function, and decrypt the input securely inside of an SGX enclave, and run the computation, and then commit the input back to Ethereum in a callback function, essentially. So that's kind of how it works right now. It works, but there are some limitations, obviously. We haven't released it in any kind of public testnet, so it's in its current form, it's like a Docker network that you can use, and it works alongside with Truffle, you know, so you can run your local Ethereum blockchain. There's no concept of incentives or nodes or staking or anything like that, because it's like purely a developer release. And you know, as I mentioned, the computations that are running are functions of Solidity smart contract, or Ethereum black code deployed smart contracts. So you know, you're limited to what you can code in there, and it's also stateless. So you can only run like stateless computations so far as you provide the inputs at the time of requesting a computation task. So this is pretty much what we have right now. So it's a good proof of concept, but we're definitely like improving a lot upon that and building something more mature. So this is just a kind of a, okay. So in this section, I'm going to cover the architecture of discovery. So like our next, Enigma.next is called discovery. Okay. Okay, so again, so like what I want to do here is to walk through this diagram essentially, and I'm going to explain box by box what it means with the hope that it's the right format to give you an idea of what we're building. Hopefully it is. Maybe you tell me after if you understood something or if it's not the right format. This diagram is fairly high level. We have some more detailed documentation, but I think it should do the job. Okay, so I'm just going to run through the boxes and hopefully try to tie it together in a way that makes sense. Okay, so here you see the word secret contract. So essentially, we're building our own smart contract engine. We call them secret contracts for obvious reasons. They are meant to run private computations. So in our next version, it's no longer that we're computing functions of existing Ethereum smart contract. Like we have our own smart contract engine. So one could go and write an Enigma smart contract. We use an existing, we're enhancing existing tools to do this. So in particular, we use WebAssembly. So our smart contract engine is based on WebAssembly. It's a really interesting platform for us to work with, and also it's a good platform that extends to the future where we want to use like MPC, because it's easy, like it's a good one, so we can work with a compiler to compile for MPC and so forth. So we use that, and the smart contract language itself. What we do is we provide a Rust library to do that. So the smart contracts will be written in Rust, and we provide a library that will be used for you to, like a crate essentially, for those familiar with Rust, to provide a crate which would be useful for one to author the smart contract and structure it like a smart contract would. So basically, in this library, there are some macros or some annotations that are being used to, say, indicate where the methods of the smart contract is, and there's a particular structure that you need to respect to like store the state and so forth. So this is roughly what our smart contract engine should look like. Yeah.
So does that mean that you have to rewrite all your smart contracts from Solidity to
Right now we're sort of researching a bit some clever way to be able to reuse the Solidity contract, so that you would have an option of using either Solidity or Rust. Perhaps with Solidity you would have access to a subset of functionality, but I can promise you that we will release this on day one or not, but that's something that we're looking into. But if not, then you would have to write your contract in Rust.
I have a question about it.
Yeah.
I understand that it needs to be written in Rust for faster execution, but does it need to be done in Rust so that it can be used on the Intel SGX essentially?
No, I mean, first of all, the runtime is WebAssembly, so theoretically you would be able to use any language that compiles in WebAssembly. However, like I said, our contracts need to respect a particular format. So in Rust we offer a library. In the future we can easily write one in C++ or write one in C, or even maybe TypeScript. I think TypeScript now compiles to WebAssembly with some kind of workarounds. So we could take all of these languages that compile to WebAssembly and write a library essentially to help you structure your smart contract with that, and also including Solidity. But Rust is kind of our favorite language. That's the language we use to write our program also, and it's going to be sort of the baseline language to write smart contract. But obviously we can extend it to anything, because WebAssembly is for those who aren't familiar, WebAssembly, it's kind of similar to the Java virtual machine, something like that. It's our LLVM. It's a generic execution environment, and it's been built by Mozilla at first, and it now ships with most major browser as a standard. So it's actually it ships with Firefox and Chrome today, and it's being used to run some system programs in the web browser, and there are other blockchain projects that are using it also. It's a really good runtime environment that's fast, that that's easy to target and so forth. So anyway, one of the key characteristics also of the smart contract, of the secret contract, sorry, compared to the smart contract function implementation that we have right now in NVT, is that our secret contracts are going to have a state. So you'll be able to write a secret contract and let's say save an attribute. Like suppose it's a class or suppose it's like a Solidity smart contract. You can save an attribute and use it later when say another user wants to execute a function on the same secret contract. So, and that state will be encrypted. So we'll have secret contracts with a state that is fully encrypted. And because of some efficiencies, it's going to be able to contain a lot more data than say an Ethereum smart contract. So you'll be able to like store more data than you would on Ethereum in the state, and it's encrypted. Yeah. Who's doing the encryption? Yeah. So essentially, it's this guy. So like the way it works is we have some keys. So each, come on, because I don't want to jump too fast. So okay, let me jump here right now. Yeah, I think I can do it now because that's where I was going anyway. So okay, this guy here, the worker, the worker is like a node of our network. So essentially what we're building is a network with multiple nodes, and it's a decentralized network, like similar to a blockchain, but it's not really a blockchain because it doesn't have a ledger and it uses Ethereum for final consensus. So it's more like another network which works alongside with Ethereum. And each node of the network, we can call it a worker, and each worker has an SGX enclave, and that worker has some keys. So essentially, like the way it works is we have, just to simplify it, like each smart contract, each secret contract that's being deployed on the Enigma network originates a new key. Let's call it a contract key. So every time you deploy a secret contract on Enigma network, there's a new key that's being generated for that secret contract. And that key is being used for two things. One, to encrypt and decrypt the state so that we could store data about the state outside of an enclave in regular storage on the worker's computer, and it's securely put in there. The other purpose of it is to decrypt the inputs. So say I'm a user here, I'm the DApp user, and I want to send a computation task. So we call it like, the terminology we're using is basically a task. So a task is like, think of it like a transaction on Ethereum. It's essentially the equivalent of calling a function of a secret contract. So whenever this guy here sends a task, first of all, he's going to send a task using presumably, like we're building a JavaScript library, which is an extension of Web3. So presumably he's sending a task using JavaScript in whatever way, either with Node.js or on the browser or whatever. And he's going to encrypt the data from here. So there's a key management process where he's going to go to the node of the Enigma network that he's connected to and request the encryption public key. And the way that the encryption key works is that the private key of that contract encryption key is always locked inside of an SGX enclave. And I'll explain a little bit more what an enclave is in a second. But it's always locked inside of an enclave, and it never leaves it unless it's encrypted and it goes to another enclave. Yeah, go ahead.
Yeah, but that also means that you have more of like a distributed encryption network rather than a replicated encryption network, since you're not sharing keys. No other node will be able to be encrypted.
No, that's not correct. So essentially, we are sharing keys. Like the way that we're sharing keys is we're sharing keys amongst all of the nodes that have been selected to work on a particular contract. And I'll explain a little bit later about how the worker selection stuff works. But when I'm saying that it's locked in the enclave is because when we're sharing the key, we're sharing it like enclave to enclave. And in transit, it's encrypted. So no one can decrypt encryption private key other than an enclave. And as far as the user goes, what it receives is the encryption public key. And what it does is that it takes this encryption public key, and it generates its own key pair, so like its user key material. And then what it does is that it derives a key from the encryption public key and his own private key, and that's how he encrypts the data. So as a result, the data that's being sent for computation from the client can be decrypted either by the user himself or by any node of the network that has the encryption key. Okay. Hopefully that makes sense to others. That was because I just explained a little bit what the worker is. So essentially, like, think of essentially our network has nodes, a little bit like Ethereum has multiple nodes, and the concept of a worker is basically a node that's being selected to work on a secret contract. And for the purpose of this conversation, let's assume that, so I'm going to explain how the worker selection stuff works. For the purpose of the conversation, let's assume that only one worker per smart contract gets selected at the time. That's not true, but it helps understanding the concept, and then I'll explain the differences at the end of the presentation. But let's assume for a moment that for every smart contract, there's only one worker selected at once to work on it, which means that if you create like this, I don't know, voting secret contract and you deploy it on Ethereum and you're a user and you start sending tasks to the Enigma network to do work on this voting secret contract, then that means that predictably there's only one worker that's going to work on this, on all of your tasks, and it's the selected worker, and you can know who it is, and you can verify it, and so forth. So what we do is that for each epoch, which is essentially it's a configurable number of blocks on Ethereum, we change the worker who's assigned to a contract. So every epoch, essentially, we rotate and we select a new worker to work on each contract. Actually, it's a group of worker, but like I'm going to present as if it's one now, just for simplicity's sake. So that's the concept of worker. Essentially, a worker is a node of the network who's been selected to work on a particular secret contract for a period of time. And what determines so essentially, like, you might ask, okay, you have 100 nodes registered in the Enigma network. What determines which node gets selected as a worker when? And essentially what we do is we do a random selection weighted by the amount of ENG token staked by each of the nodes. So if you want to register to be a node in the Enigma network, you have to stake some ENG token, and the more you stake, the more likely you are to be selected as a worker. And then when you get selected as a worker, what happens is that you get the computation fee, so essentially the gas that each users pay to run the computation, essentially. So if I'm a node and I stake a lot of ENG, I might get picked as a worker frequently throughout the day, throughout the week, or whatever. And whenever I'm picked as a worker for a period of time for each contract, any task that comes in directed towards a contract that I'm the selected worker for, I get all of the gas associated with that, essentially. That's how it works. So that's how the worker selection stuff works, and also that's how the economics work. Yeah.
Where does the registry of the workers?
It's on Ethereum. So essentially, we create a kind of an Enigma registry contract on Ethereum, and that's what.
You use the registry to randomize?
Come again?
You randomize within that registry, or the randomization seed is produced somewhere else?
The randomization seed is produced somewhere else, and what we use for randomness, essentially, we use a property of SGX that allows for randomness. So one of the properties of SGX is kind of they call it like a true randomness. Essentially, it uses the current of the chip to produce a random number. And so we use that. And right now, in our current implementation, this is temporary, but like right now we have one node that would generate a random seed for the rest of the network. This is kind of just a stopgap, but what we're working on is to have some kind of a consensus where multiple nodes might bid a random number, and then something else which is more inherent to the network determines which number is being picked. So like our goal is to generate like multiple random numbers from multiple enclaves, just in case, like just on the remote, you know, probability that an enclave gets compromised somehow.
Right, but then the problem here is that if I somehow predict, if the seed, where the seed gets generated is predicted, then I will attack that, right? So better model is to have multiple random seeds and then combine that with
Yeah, that's what I'm talking about. Yeah, yeah.
But then further on, isn't it a good idea to use the existing workers to supply the randomness and take that?
Yeah, you're correct. Like we haven't exactly defined the economics of random numbers because, like I said, right now, like we're using this kind of a stopgap method where we simplify it with one node. But you're correct. In the future, there should be some reward for generating these random numbers. Yeah, or maybe it's a cost of business. Like if you don't, then you don't get picked, you know, in that epoch or something like that. But there will be economics tied to your obligation of generating a number. Yeah.
Okay. So, I mean, how many workers can there be in this
Come again?
how many networks can there be in this work? This network? Is it like global scale? Or
Yeah, it's infinite at the moment. We don't have any. We haven't defined like a minimum sort of staking amount, right? Because remember, to be a worker, you have to stake some ENGs. So we haven't defined a minimum. Like we probably will, so that someone doesn't come in and stake like dust of ENG and stuff. But you know, it's not going to be a high. It's not going to be a high barrier of entry, essentially.
Is there any penalty for dishonest nodes? And is there any like validators that check the work that's done by the computation to make sure it's accurate?
Yeah. So the penalty, we're still working on that a little bit. So I can't give you like an exact protocol, but we've thought about it. We're looking at different ways of doing it. I have to say we're using SGX Enclave, so it's not like we're like this gives us some guarantees as long as the enclave is genuine. You know, we have some guarantees, and then what we're doing is that we have multiple workers, and I'll explain that at the end of the presentation. Basically, we have some internal consensus algorithm that we use to allow multiple workers to compute each tasks. So instead of like picking one worker, as I'm kind of presenting here for simplicity, we have multiple workers computing each tasks, and that allows us to do like some kind of a voting, so that if one worker gives a result that is different from the others, then we'll be able to catch that, essentially. So that's how the validation works. It's like an internal consensus on each task. Yeah.
So there's different workers kind of verifying the same contract, or is it voting?
Yeah. Yeah. So yeah, essentially like we have, like right now I'm explaining as if there's one, but we're working on this kind of internal consensus so that multiple workers can act as one, right? So every time that selection is being done, like so for every epoch we reshuffle the workers, we're going to select multiple workers per contract, and that group of workers is going to essentially validate each other. So they're expected to all come to the same result, and if they don't, then you know we'll be able to catch any false results. But also we also rely on SGX a lot, like, to prove certain things about correctness. That is not just like this kind of interactive verification of the results.
Then you must know, of course, you know, the foreshadow attack, the side shadow
Yeah.
attack, that SGX is, you know, given the current state of SGX is must be perfect.
Yeah, we know that. I mean, so like there's a couple of things I can say about this. So first of all, these issues are kind of open research item. I mean, we're working really closely with Intel, so we're trying to at least know what the state of these things is. So at least we're aware of these attacks and just the state of research around SGX. Also, like, we're trying to do things to minimize the severity of, say, one of these workers or multiple of these workers being compromised in that way. One of which is to externalize the key management module so that workers only get sort of the contract keys for a limited amount of time, basically only when they're being selected to work on that contract, and not the rest of the time, so that if there's an attack, then at least the damage are kind of limited. So like we're thinking that angle as well. And obviously the third angle is the MPC angle, where our first version isn't going to include MPC for computing each task, but this is something that we're working on right now, and it's kind of a top priority, right? So if you had the computation being done, say, by 2 workers with SGX, but also in an MPC fashion, where the computation is split and not one enclave has all of the data, then that becomes a lot more robust. And there is also a benefit of using MPC with SGX, because SGX still gives us some strong guarantees so that we could have some smaller clusters and still be still have a strong security there. So essentially, like, our goal is to basically combine both. We're starting with SGX, then we're moving towards MPC, and we think that having both makes a stronger solution than just having MPC.
Wait, what's NPC?
MPC is a multi-party computation. So in a nutshell, and I'm not the MPC researcher, so some of you guys might know more than I do about like the details of it, but essentially, like, conceptually, the idea is to take one computation with data and so forth, and to be able to split that computation into multiple chunks, where not one chunk has all of the data. So if one could have access to one of the chunks, it still wouldn't contain the full puzzle, so that still no crucial information will leak. So that's kind of what MPC is in a nutshell. So with the idea of having multiple workers, then we can extend that so that instead of each worker computing the same thing, then each worker computes a chunk, and then the results are aggregated at the end. So that means that if an enclave is compromised, then the data that leaks potentially is harmless. Yeah.
So when you talked about like having multiple workers basically do the same computation, so essentially are assigned to the same contract. So if that's encrypted, then like how does the user like essentially provide the key to encrypt and decrypt that?
I have a
how do they like come to agreement?
yeah. I have a slide about this at the end, so I can cover it at that point. Does that all make sense to you guys so far? Or? Yeah. Okay. So, all right.
I just had one question.
Yeah.
There's something in cryptography called like homophobic encryption, where it's like
Homophobic?
homomorphic.
Yeah.
What is homomorphic encryption, where you're performing like computation on encrypted data.
Yeah.
So in this situation, are you guys using that sort of cryptography, or is it just depend on the Intel SGX nature?
No, I mean, I'm not a cryptographer. My understanding is that this type of encryption isn't necessarily ready for prime time right now. It has kind of limited applications. But I think we're doing the second best thing, which is to combine secure multi-party computation with enclaves once we get to that point, so that we can have secure multi-party computation, and on top of that, each of the participants are secured by hardware. So we think that it's probably as good as it gets in terms of encryption. But if you're aware of someone that has a general purpose technology that allows to do what you're talking about, then we'd like to know about it.
Is working on it, or I think they have it on the customer.
Okay.
Really? Yeah.
Yeah, I mean,
They're not telling you.
But is it is it optimized for a very
yeah, we'll definitely experiment with that and see like what the limitations are. I'm sure there are some. Okay, so all right, moving on. Okay, as I mentioned, the users, the DApp users, they use this JavaScript library and then they send computation tasks to the network. And one thing that happens when a computation task is sent to the network is there's also a task record being created on Ethereum. So essentially, like sending a computation task to the network is kind of a two-step process. First, there's a record being created on Ethereum, and this is a very small record that contains just a couple of hashes. And we use that so that we can use Ethereum for like to order the task and also for final consensus. So like if something is submitted to our network, we always validate against this task record to make sure that this task record exists. So that's like our current integration pattern with Ethereum. And the other thing you can do with this task record is you can attach some ERC20 tokens, for example. So in our secret contracts, we have some payable function that might accept like any ERC20 token. And the way that you would pass these tokens from your Ethereum wallet to like the Enigma secret contract is by attaching them to this task record. Of course, this is being done transparently. Like we have a JavaScript library that makes it kind of seamless, but that's essentially what's happening behind the scenes. So if you want to use the Enigma to like transfer some tokens, you can. We can put rules in secret contracts that tokens are going to be transferred to another address or call functions of Ethereum smart contracts. And this is being done by essentially depositing the token in the Enigma registry contract using these task records. So so each task on Enigma, at least currently, does require a transaction on Ethereum. These task records can be created in batch. So if you have an application that kind of has to do multiple computation at once, then it could create a batch of task records, so sort of to speed up the process and also minimize the gas and stuff like that. We're looking at ways that maybe like even we could, and that's not going to be out for the first version, but looking at ways that maybe we could use delegates also like to execute these transactions. Like so perhaps the user just signs a raw transaction and then someone else commits that record to Ethereum, but that's not for now. So essentially that's how it works. So like the task record is kind of the record, the official record of a task, which is stored on Ethereum. And then each DApp user, well, actually, I'm going to show you the next diagram. I think it explains this better. All right. So sorry about that. I'm gonna talk more about this process of sending a task in the next diagram. But first, I want to talk about a little bit like how SGX works. So essentially, one essential concept of SGX enclaves is this notion of a remote attestation. And this is critical, at least for this current SGX implementation, because remote attestation is what we rely on to ensure that the workers who are running the computation are kind of safe, so to speak. So the way it works is each node that will register to the Enigma network as a worker will have an enclave, essentially. So to run Enigma's client, to register as a node, you need to have hardware with SGX enabled. SGX is available on a lot of the recent chips, Intel chips. I think from 2005 and on, some of the most recent chips have different features. There's actually a key feature on the 2018 chips that I'm just going to touch upon. But essentially, which is not going to be required initially, but it's going to be very handy for us. So essentially, you need to run the node application, you need to have this SGX enclave enabled on your computer. There are some cloud providers that offer it, Microsoft, Azure, and also IBM Cloud, or whatever that's called. So if you want to be a node, you have to have one of these. And also you need to have a EPID associated with your enclave. So an EPID is an identifier that kind of uniquely identify your enclave, essentially. So these are the requirements kind of to be a node of the network. And then essentially what happens is that when you register to the Enigma network to be a node, essentially you do that by sending a transaction on Ethereum, because as I mentioned earlier, like the list of available workers or nodes are being tracked in a smart contract on Ethereum. So what you do is that you go through this process defined by Intel to get a report. It's called a report. And essentially the way it works is that we've written software to help with this. Like in our Enigma client, there's software that facilitates registration. So what you would do is that you would run the registration process in the software that we wrote. Then what that's going to do is that it's going to produce what's called a quote in your enclave. So an enclave that wants to be sort of authenticated produces what's called a quote, which is just like, you know, a cryptographic proof of some kind, which is produced by the enclave and signed and everything. The enclave produces this quote, and then what we do is that we send this quote to this ISV server, which is hosted by Intel. So the purpose of this is that an SGX enclave produces a quote, sends that quote to Intel, and then Intel returns a report that says, yes, this is an authentic enclave, and it also offers other guarantees, like, for example, making sure that the code that runs on the enclave is only the code that's supposed to, like the Enigma client, for example. So basically, you send that quote to the verification service of Intel, you get a report in exchange, and that report is what we're committing to Ethereum during the registration process. Right now in our MVT, the verification of that report is done by each user before submitting a computation to the network. So before submitting a computation to the network, each user knows which worker is going to pick it, so can verify it up front. But we're currently working on an on-chain verification mechanism, like using an RSA library for Solidity. So unless, if all goes well, like the plan is to be able to, unless we hit some road bumps with this, the plan is to be able to verify these reports as each node registers as a worker to the network. So essentially you get that report from Intel and you send it to Ethereum as part of a special transaction. Ethereum does some cryptographic stuff with it, which is basically verifies the signature that's embedded in the report, verifies that this signature is valid and contains the data it's supposed to contain, and also does an SSL root chain to make sure that the certificate, each certificate is like an X509 certificate, so you can do a root chain to make sure that the report is an X509 certificate, so you can do a root chain computation to make sure that this X509 report certificate came from Intel's, CA trusted certificate and so forth. So basically, that's how it works. I know I'm explaining this in a convoluted way, but essentially, this is like an important cryptographic guarantee that we have, because once we've done that, once we got the report from Intel and verified it and put it on the blockchain, the data that we're actually verifying with the signature is like an address, which we call the signer address, and then we know that afterwards, any computation, any proof that's being sent to Ethereum, which we call like a task receipt, so any proof that's being generated after computing a task is being signed by that address. And that's how we're kind of confirming that each computation have, in fact, been executed by an enclave which hasn't been tampered with, which contains Enigma's code and nothing else, and so forth. So these are the kind of guarantees that we're relying on this right now with this. And what I wanted to say, this is very exciting because Intel just released some spec and some information. I read it. I have to read it like more than once, like to fully understand all of the details of it, the implementation details. But they're kind of getting rid of the requirement to do this. So right now you have to use this sort of centralized Intel server to verify your enclaves, but in the near future, I think starting now with the chips that have been manufactured in 2018, you'll be able to delegate other entities, presumably some of the worker registered on the Enigma network, to do this verification. So Intel has built this library to be able to implement that and basically do that outside of just the ISV server of Intel. So that's really good because it allows to decentralize this a lot more and not rely on some kind of centralized server to verify the enclaves. This isn't going to come in version 1, but the specs are already out, so like we're working on implementing it, and it's going to be there like soon.
Is this verification process something that only happens once, or does
Yeah.
every node like have to redo that or something?
No, it happens once. So it happens once, and as long as you sign your proofs with the address that's been verified, then you're good.
What if like the enclave gets compromised at some later point? Like you would still be signing with the same address, and you would still claim that they're down. Right?
I mean, I guess it depends on what you mean by compromise. Like if the enclave gets compromised to the point that your signing key, like the native key in the enclave, is leaked, then we're in trouble. Like all bets are off, basically. Because that signing key is very critical. Like this is what allows the enclave to prove anything. So if that signing key is compromised, then that's no good. So yeah.
How is that possible?
I don't know if that's. I don't think that's possible. I don't know about the last attack. I think it's not possible, but I'm not sure. If you guys know otherwise, just let us know.
The attack risk records. So what they blocking this
Yeah. Yeah, until recently, like all of the side channel attacks that had been found, like were kind of limited in scope. But there's a new one that's been found like last month, which is a bit more severe, that could potentially leak the signing key, but I'm not sure about that one. And again, I'm not the one following up on it, so I don't know all of the details. Guy, our founder, is much more deeply involved with this, but I think the last one is pretty bad. So we'll have to make like basically this is gonna have to be fixed one way or the other, or someone is gonna have to prove that this is only a theoretical attack. But right now I'm not exactly sure what the status is of it.
I'm understanding side channel attacks leak data, but not keys.
Yeah.
It doesn't leak keys, you leak data.
But again, it's theoretical that essentially you might be.
Okay.
Yeah.
We haven't done enough research in the side channel attack to understand the principle.
Yeah, that's my understanding as well. So I guess we'll have to see. But if the keys leak, then there's a big problem.
The idea is the inherent problem with the GX is in architecture because they share the resources, right? The underlying resources are shared. So that's where the attacks the side channel and core channel.
Okay, so this diagram here just explains with a little bit more details. Like this is kind of explaining the life cycle of a task, right? So how does a task get created, and where does it go, and how does it get completed or verified? So this is what I was trying to explain earlier, but I think this diagram explains it a little bit better. So essentially, for each computation, the user, the DApp user that wants to originate each task will create a task record on Ethereum, plus provide the task input. So the key thing here is that on Ethereum, we're not storing the input of the computation, we're just storing a hash of the inputs, which from that record you will be able to know if the inputs that you're seeing coming are the right ones or not, but we're not storing the inputs themselves. The task inputs are being encrypted by the DApp user, like in the using the protocol that I described earlier, and sent to the Enigma network directly. So the way that the Enigma network works, again, it's like it's a connected network of nodes. We're using libp2p, for those familiar with it, to exchange messages in the network. So the way that would work is that the DAP user would be connected to a particular node of the network, will send his encrypted input to that node, and then that node will propagate these to other nodes until essentially the selected worker gets them. So we're using the network to propagate the inputs in that way. When the selected worker or workers get the input, then that worker would have the encryption key required to decrypt them, as I was explaining earlier. And also, that worker will be able to access the state of the contract. So the way it works is that each contract has a state, as I mentioned earlier, like you can save some attributes of a secret contract. And the way that these attributes are being saved is in the form of state deltas. So every time that a worker executes a computation, there are side effects essentially. These side effects are like for each computation, you may have essentially outputs, like a return statement. So for example, if I'm a user and I create a task, meaning calling a function of a secret contract, that secret contract might have a return statement where we want to return some values. So these are the outputs of a computation, and these outputs will go back to the DAP user. So essentially, these outputs will follow the reverse encryption scheme. So these outputs will be now encrypted using the user public key and the private encryption key, or a key derived from the user public key and the private encryption key, and flow through the network back to the node that the user is connected to, so that the user can access those outputs. So basically what's being returned by the return statement of the function of the secret contract specified in the task. This is for the outputs. But also, if your secret contract has a state, so has some attributes that store some values, like in the case of a voting contract, I don't know, like there might be everyone's vote, and you don't want to return that to the user every time, so you want to keep it in the state. So what will happen is that we're calculating a state delta. So the worker knows the current state of the contract. So for this example, let's suppose that it's a brand new contract and I'm sending the first task that goes in this contract. So the state of the contract is empty. So what's going to happen is the worker would have like an empty state for the contract, and then I send a task, the worker computes it, and the function that's attached to the task includes some business logic that modifies the state. Then what would happen is a state delta will be generated. And the state delta is like a patch. Essentially, it's a CRUD operation against the state. So it will specify like whether some data was added to the state and where and so forth. And what we do is that, one, we keep this in memory until the worker is the selected worker. So basically, like the worker always keeps a copy of the state in memory so that when it receives the next task, it has the latest state. But also, we encrypt the state delta and dispatch it across the network. And that's how the state is stored, essentially. So each node who might, and there's a process to determine which node gets which delta. I don't want to go into that right now. But essentially, like each node that receives the state delta for a given contract will store like a bunch of encrypted state deltas. And when that node is being selected as a worker for this particular contract, it will take all of its state delta. It will say, okay, I just got selected as a worker. An epoch just ended, I got selected, now I'm gonna perform computations for this particular contract. Then the worker will take all of the state delta that it has in storage encrypted and replay them in the enclave and essentially reconstitute the full state in the enclave. So the decrypted state is only available inside of an enclave and never outside. And the data that's stored outside of an enclave is an encrypted state delta, which basically is CRUD operation against the state that you can replay at any time. So that's kind of how it works, like with the state. So that's what I'm saying. Every time there's a computation, you may have two side effects. One, the results. Two, the state deltas. and I'm kind of trying to explain how these are being handled. There's another side effect that can exist that I didn't model in here. I probably should have, but essentially another side effect might be Ethereum calls. So in our smart contract language, we're allowing, for now, we're only allowing this as the last line of a secret contract function. Like for obvious reasons, like we don't have yet an asynchronous like way to go in and out of a function, but essentially like at the end of a secret contract function, you are able to call an Ethereum contract. So this is very useful because, say for example, you have, I don't know, some TCR application already on Ethereum, and you want to use Enigma for specific things, like maybe to tally the votes, then you want to be able to return the result straight to your Ethereum contract and not have the user receive it and trust that he's going to commit it. So you want to be able to sometimes send computation results straight to Ethereum. So we allow that. So our smart contract language allows to call an Ethereum function at the end, and you can call basically any function of any smart contract loosely, I guess. Like, yeah, as long as it's a public function, it will work. And you can also, that function can also accept ERC20 tokens, because as I mentioned earlier, it's possible to kind of lock ERC20 tokens inside of a secret contract and kind of unlock it later in that manner. So if you do that, if you have this kind of call in your secret contract, there's going to be a third side effect, which is going to be essentially a list of encoded Ethereum calls. So that's going to be a kind of a third type of output coming out of your computation task. Now, okay, so now this is defined. So we have our task, we know what the inputs are, we've defined what kind of outputs are there. Now, I'm going to introduce the concept of batch. So essentially, first I'm going to talk about the use case where you don't have these Ethereum side effect, like you have computations that don't call Ethereum. Suppose that's the case, then what could happen is during each epoch, a user could go and send like 5 computations to the network. For simplicity's sake, let's assume there's only one worker, but this also works with multiple, but like, just assume for now there's one worker.
Sorry.
Yeah.
Sorry, can we define an epoch?
An epoch is a number of blocks on Ethereum configurable.
Exactly. So how do you pick an epoch?
We haven't necessarily picked the length yet. It's going to be like a parameter when the contract is deployed.
Is that are you finding it because you want to make sure that the finality aspect, there is something that you need to do, data that you need to have to address an issue of finality. So as you're picking an epoch, that's sort of the data that you finalize from whatever block.
I think, I'm not sure, like basically the purpose, like the finality is basically done on Ethereum, right? Like that's our final consensus. And the reason why we have epochs is to be able to rotate the workers, because otherwise, like you would pick, say, it would be always the same worker, or it will be always the same group of worker per contract, and there will never be rotation. So if you got lucky enough to be selected as the CryptoKitty on Enigma, secret contract, you're gonna make tons of money, and it'll be good forever. So that's kind of the reason why we have these epochs. It's actually complicating things in terms of finality because the epochs end, so we have to make sure that the tasks that were assigned during that epoch get finalized, and there's some complications associated with it, but that's the reason why we have them. And ultimately, a batch might exist within an epoch, like we don't have batch across epochs. And the purpose of a batch would be that if my users submit many computations to this, let's assume there's only one worker selected for now, to this one selected worker, then this one selected worker can compute all of these tasks sequentially without having to report to Ethereum every time. So that allows that worker to compute stuff much faster because you don't have to always rely on Ethereum for consensus. So essentially what will happen in this case is that the task will be sent to Enigma, the worker will compute them, and the task output will go to the user as soon as they're completed. So the user will be able to get the results like fast, even before they're confirmed on Ethereum. And then once the batch closes, and there are two events that will essentially force the batch to be committed on Ethereum. Either the epoch ends, or one of the tasks that's part of the batch has one of these Ethereum calls. If that's the case, then the network will take all of the tasks that came before that task that has the Ethereum call and then commit them as a batch. So that's kind of what defines when batch are being committed. So it's still going to be committed pretty frequently, presumably, because we have to account for these Ethereum side effects. So it's not going to be just one per epoch, but it will be a lot faster than if we had to commit every single task on Ethereum for consensus. Yep.
If I'm the owner of a contract, and I execute like the only the owner can do, does this lifecycle change in any way?
I don't think so, but can you? I don't understand. I guess the use case that you're describing.
Oh, for example, so if the contract, secret contract is a USD contract, or a tokenized store, for example,
Yeah.
and I want to see who owns what, would this be exactly the same? So like hold the contract same way.
Yeah, there's no like real differences between being a contract owner or being a user. If you're a contract owner in your secret contract, you may have some modifiers, like on Ethereum, so that only you can do certain operations, but the flow of a task isn't going to be any different.
Because when you open the contract, you don't have any, you don't have the private key for the contract.
No.
You don't have anything.
No human, and that's the point, right? No human should have access to the data, and that's a really critical point, because otherwise it's no better than an AWS server where the admin has access and might leak it on the darknet or something like that.
Actually, kind of, my question actually based on top of this question, I think, a little bit. Are the public addresses in Ethereum available in the secret contracts?
Yep. Yep. Yeah, there's no, like at the moment at least, in the incarnation of our network, like we're kind of like we're building some building blocks, and eventually like we'll have our own ledger, but right now we don't. So there's no concept of an Enigma address. An address is an Ethereum address, but you can reference it in Enigma's secret contract. And the reason why we're building it this way also is like we really want to be a very usable solution for existing Ethereum dApps that you can kind of put in, and it's fairly transparent for the end user. So that's why we don't have like these separate deposits, these separate addresses and so forth. Like we try to make it as much as possible to send something that looks like a regular Ethereum transaction, but that's private and that can contain a lot more load, like contain a lot more data, a lot more extensive computation, and we can run it.
We're at 8:30. I want to make sure you get through all the content. So if there's other questions, I can ask you guys to hold them until we're at the bar. I just want to make sure that we get through all the content.
Okay, sure. Yeah. Okay. So.
As quiet as possible, because you can hear them throwing away our pieces.
Okay. So.
I mean, if everyone's happy to stay, we're happy to stay.
Yeah. Yeah, I'm pretty much, I think I'm done with like all of the key concepts. I just wanted to flash this diagram quickly, which isn't very detailed because frankly we're still working some of the details on this, but this is basically representing the internal consensus that we have because so far I was trying to assume that there's only one worker selected per contract per epoch, but obviously that's not the implementation that we want to go for, it's multiple workers. So we're building this kind of consensus where multiple workers can be selected to work on a contract at the same time, and essentially what will happen is that they would share these state deltas, like basically they would all run the computation, share the state deltas, and in a way that does something like a proof of replication, where we have some properties of the consensus that ensures that every node selected actually got the state deltas and can cross-validate and so forth. So I don't know if I want to, if I need to provide a lot of details on that, but essentially this is an interesting problem that we're currently working on to grab a pretty good solution for it. That will allow us to use like multiple workers kind of working together as one, and this kind of consensus is super fast. So that will be pretty good. So we'll be able to have multiple workers, and what this prevents is, for example, if we had just one worker per computation, then there's two major issues with this. One, that guy could decide to go offline and you never hear from him, or it could decide to throttle the computations, or maybe it could be compromised. Where with this, if a worker doesn't sign the messages fast enough, then it's just dropped from the cluster, and the other workers continue working on the computation. So this is a way to incentivize workers, like to basically.
Would a new worker be assigned? The worker is dropped.
I actually, to be honest with you, we haven't finalized that detail yet as to whether we need to assign a new worker to a group, or if we just continue the group like handicapped by one. I don't know. It's not the final decision yet. So yeah, that's pretty much it for me. I think covered all of the essential.